Hello, welcome back to the course again on biomedical ultrasound, fundamentals of imaging and micro-machined transducers. This is Srinivas Bhaskara, TA of this course. We were discussing about thermal oxidation and in the previous lecture we have covered multiple topics. If you look at the slide, we discussed about dry oxidation, wet oxidation, different aspects, and if you get X thickness of silicon dioxide, whether how much is consumed, silicon is consumed or something like that, okay, all those things we have seen. And then we have also established the basics that are required for understanding Deal-Grove model. Now here this is where we stopped, so if you look at it, there are two flux. Actually there is one more flux in the ambience, right. There is one more flux in the ambience, but we are neglecting this because we are thinking that there is infinite number of molecules are available for that, right. So now let us try to model one by one, right. So I have flux 1 which is a diffusion flux, this is minus d dou c by dou x. If I recreate the picture, you have silicon, this is the thickness, right, and okay, just a minute, let me redraw this again. So let us say this is silicon and we assume that some oxide is formed for our understanding, right. So this is silicon dioxide. What we thought is the molecules has to diffuse to the interface and then react, right. So there is flux 1 here and at the interface there is flux 2, right, which is getting oxidized, right. Now let us say this concentration Cg, this concentration is Ci, right, and I told you about Fick's law, F1 is given by minus d dou c by dou x minus d, and if I assume this thickness as x, okay, then what is the concentration, final minus initial, Ci minus Cg divided by x. So very simply this is d Cg minus Ci by x, right. So what is F2? This is the flux at the surface that is getting oxidized, Ks into Ci, because here the flux the concentration is Ci, right. So what is F3? Very simple, okay, the ambience flux we are neglecting because oxygen in oxygen, water in water, so much will diffuse, right, that will not be a bottleneck, right. At equilibrium F1 is equal to F2 is equal to F, we understood also how it will happen, right, at equilibrium, right, both has to balance out each other, right. So then the rate of growth is given by F by Ni, right. So this Ni, don't worry, this is just a number, right. So this F is equal to F1 F2, I can say Ks into Ci by Ni, right. So now if I can solve this equation 3, okay, this is equation number 1, equation number 2, equation number 3. Now generally what is known is what is on the surface, that is known, right. See, this is Cg is decided by the solid solubility limit, okay. What is this guy, okay, what is solid solubility limit, right. Now if you have a glucose, for example, if you might have tasted the glucose anytime, right. If you take 100 ml of water, right, 100 ml of water if you take, right, typically if I remember correctly, you can only dissolve 9 grams of glucose powder, right. If you put more, what will happen? It will precipitate, okay, it will not get dissolved, right. Now suppose if you increase the temperature of the solution, then you can dissolve more, right. So this is a typical concept of understanding solid solubility, right. Now in the similar way, silicon, how much silicon dioxide can handle, right, depends on the temperature, at what temperatures you are operating it. Higher temperatures, higher, right. This is also one more advantage of operating at higher temperatures, right. Now, why wet oxidation is very high, very how we will get very thick wet oxide films is because, right, the solid solubility of water is very high compared to solid solubility of oxygen in SiO2. Okay, this could be your assignment question. So, I am just erasing this part. Okay, I am just giving a hint, okay, why you get a thick oxide films using wet oxidation than dry oxidation, right. So, right. So, solid solubility limit. So, there is a limiting factor, there is a limit on the number of atoms or molecules that can be diffused through the silicon dioxide, right. Cg is the limit, right, and Cg is typically known, okay, this is known, this is known, this is known for every material inside silicon dioxide is known, but for Ci is not clearly that much known, right, it is very difficult, it is random, correct. So, better if you can get Ci in terms of Cg using this equation, right, you already have this equation there, right. So, if I make equation 1 and 2, if I equate them, right. So, equation 1 is d into Cg minus Ci by x, that is equal to Ks into Ci. Now, d into Cg minus d into Ci is Ks x Ci. So, now if I can rearrange, dCg is equal to Ks x plus d Ci. So, what is Cg? What is Ci now? What is Ci? Cg divided by d, I mean d into Cg divided by d plus Ks x. So, what is Cg now? Ci now? Cg divided by this d, if it comes to the denominator, 1 plus Ks by d x. Ci is Cg divided by 1 plus Ks by dx. So, if I substitute this in equation number 3, so dx by dt is equal to Ks by Ni, so keep it outside, right. This is Cg divided by 1 plus Ks by dx. You understand now how the equation has changed, right. Now, if I can rearrange these terms, right. So, Ni like dx by dt 1 plus Ks x by d is equal to Ks into Cg, right. Of course, there is a Ni here, right. So, I am just trying to rearrange so that I can integrate easily, right. Now, if you integrate this part, right, just a minute, I will try to rearrange it very nicely. Let me take my red pen, red color, yeah. So, Ni 1 plus Ks by d x dx by dt is equal to Ks into Cg. Right. So, in a standard form you can send these guys out and then send this guy here, Ni 1 plus Ni by Ks Cg 1 plus Ks by dx is equal to dt. Now, if you integrate this equation, so what will you get? Okay, I am neglecting the, I am making it very simple. You can have initial conditions later, assuming that there is no initial conditions, nothing, right. So, what you will get is Ni by Ks Cg into dx. If you integrate, it will become x plus Ni by Cg Ks, this is Ks by d into x dx is x square by 2, that is equal to T. Okay, if you have initial conditions, you have to write xf square minus xi square, then T plus tau, on the left hand side xf minus xi, something like that. Okay, I do not want to complicate the matter right now. This is just for you to simply understand what exactly is this, right. Now Ks gets cancelled here, and let me erase some part of this on the right side. This anyways, now we are sure about it, how we are getting to get the equation. Just erase this part. Now it will turn out to be a beautiful, why am I trying all this, okay, just it will turn out to be a beautiful equation, okay, quadratic equation. So what happens is, this is Ni x divided by Ks Cg plus Ni divided by 2 Cg d x square, that is equal to T. So they beautifully converted this into this form, okay. So this is like x square by b plus x by b by a, that is equal to T, okay, d will not grow, right. So if you look at this, b is 2 Cg d by Ni. It makes sense to write like this, okay, otherwise it will become very easy to understand, right. What is b by a? What is b by a? This is Ks Cg by Ni, right. So if I take a new slide, so what I wrote is x square by b plus x by b by a, that is equal to T, where b is what? B is 2 Cg d by Ni, 2 Cg d by Ni. B by A is Ks Cg by Ni. Okay. Now if you look at these two b and b by a, right, let me take another color, okay. Cg by Na if you ignore, right, in both the equations Cg by Na is there. B depends on the diffusion, b by a depends on the Ks. That means somehow b connected to the diffusion, b by a connected to the reaction rate. Somehow this b by a signifies about the reaction. That is the reason why we did all this okay, kind of rearrangement, shuffling and all those things, right. Now does it make sense later? Let us see. Now you have this equation, this is a quadratic expression, right. So the growth is not going to be linear, that is very clear, right. Now what is x now, right. So let us say you have an expression ax square plus bx plus c equal to 0, what is x? Minus b plus or minus root of b square minus 4ac by 2a, something like this, right, which is very school mathematics, right. Now here small a is 1 by b, small b is 1 by b by a, c is minus t, okay. When this guy comes to the left hand side, it will become minus t, that is equal to 0, x square plus bx plus c. Now if I substitute for this, x is, right, minus b, right, minus 1 over b by a plus or minus root of, again b square is 1 by b by a whole square minus 4, what is a? 1 by b, what is c? Minus t divided by 2a by b, correct. Now here if you look at it, x is thickness, right, that is what we are talking about, and thickness is always positive, right. So, this will have two roots, right, minus 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 plus. So, you ignore this minus minus because that is not possible. So, x is minus a by b plus or minus root of a square by b square plus 4 t by b divided by 2 b. Right. Now, I can cancel out this as I can write as minus a plus or minus root of a square plus 4 t b divided by b divided by 2 into 1 by b, cancel out. So, x is a by 2 into root of a square plus 4 t b minus 1. Right. Okay. So, I think if everything is correct, so let me check minus b, b is by b by a by b, then a square, a will come out, here is the issue. See, when you take a by a outside, right. So, here it will become 1 plus, okay, I will tell you where is the mistake that I have done. See this point, okay. I just quickly jumped from one to another, okay. Okay, one by one will do, no issues, okay. So, take a red pen, right. Now, minus a plus or minus root of a square plus 4 t b divided by b divided by 2 into 1 over b, right. This b gets cancelled. Now, minus a plus or minus, if I take a square out, like I am neglecting the minus right now, okay, we already discussed about that. Minus a plus, if I take a outside, 1 plus 4 t b by a square, right, correct, by 2. So, what I am saying is x, that is equal to a by 2, right, this is root of 1 plus 4 t b by a square minus 1, this is the x value. Now, right. So, I will ignore the other things, okay. I will just let me erase this part. Just erase this part, right side, quadratic equation and all. Now, how to plot the x with respect to time? Is it linear with respect to time? So, if I plot, just a minute, another color, the x with respect to time, right. If let us say t is very small, then what happens? This t, this term, this will be very small. So, it will be 1 plus x power half. So, 1 plus x by 2 expansion, you know, right. So, what happens is x equal to a by 2 1 plus 4 t b by a square 1 by half, this will be minus 1, minus 1 gets cancelled, a square 1 a will get cancelled, 2, 2, 4. So, x is just b by a into t, right. Now, what is this x equal to b by a into t? How to plot it? So, x b by a is a constant, okay, at a given temperature. So, x will grow linearly with respect to time. Right. That means imagine if there is no growth, if the x are initially at t equal to 0, you do not have anything that is formed. So, whatever that is formed is because of the reaction, not because of the diffusion, right, yes or no, when at t equal to 0 initially, right. So, at t equal to 0, what exactly is formed is because of surface reactions, not because of the diffusion. That is what it is saying, right. Now, what is this b by a suggesting? What is b by a? B by a depends on what? Ks. What is Ks related to? Surface reaction. That is why this model has become very extremely popular across the community, right. Not only that, suppose if the time is very high, correct, then what one can do, right. So, you can neglect this one, right. Then if you can rearrange it, x will become like root of bt, because you can 2, 4 gets cancelled, then a gets cancelled, x is equal to root of bt. And if you look at it, x is root of bt, okay, is not linear, right, it is parabolic, that somehow it is going to saturate. Of course, there is a growth, but not linear growth, it is a non-linear growth or parabolic growth. Now, x equal to root of bt, what does b suggest? 2 Cg d by Ni. What is d here? Diffusion. You understand that? B signifies diffusion and x depends on the diffusion, root of diffusion multiplied by t, right. Also think empirically here. Suppose if there is some considerable thickness or you have kept it for oxidation for a long time, then what happens? There is a thickness that is already formed. Now, whatever the new interface that has to be formed, like silicon dioxide thickness that has to be formed, is through the diffusion. Means diffusion will decide how the increase in the thickness happens. Initially, reaction rate regime will decide how the thickness growth happens, right. Now, here the growth is decided by b by a, here the growth is decided by root b, of course t is also there. That means that in the initially when t equal to 0 and the initial phase, right. So, this is all comes under reaction rate limited regime. After that, diffusion limited regime, okay. Diffusion regime, reaction rate limited regime. So, this is very beautifully portrayed, alright. Let us understand few more aspects and then we will get into the problems. This is how it is, okay. This is how the modeling is, and this holds good for considerably larger thicknesses and the range of thicknesses and range of temperatures as well, alright. Now, here if you look into that, what I have done is I have approximated it, right. Now, what they are saying, you have a gas, you have an oxide and you have a silicon, right. Now, we have considered only this flux and this flux, ignore these terminology, okay, right now. We have said this F2, F1, F2, right. We consider this flux very high, right. Very high means that H is very high, mass transport quotient is very high, that means that this is very high, that means that this will become 0, I mean approximated to 0, right. That is what we got, Ks Cg divided by 1 plus x Ks by d into Ni. This is what we got. You understand? Because we have considered this F1 is very high, I mean like according to this notion, the flux in the in the ambience is very high, right, compared to diffusion flux and the reaction flux. That is the only difference. So, if you, I wanted to simplify it, that is why I just took 2 flux, otherwise it will become complicated, I do not want to mess it up. So, this is the equation that governs, this is what we governed. Okay. Let me check whether we got the right one or not. B is 2 Cgd by Ni, correct. Then B by A is Ks into Cg by Ni, right. Now, if you look at it, right, what can we draw, right, this is what we got, no, right, if you ignore this tau, right. Initially the growth depends on B by A, later the growth depends on B, B by A means it depends on Ks, B is it depends on D, right. So, this empirical or mathematical model will match the experimental outcomes, that is why it is very popular, right. Now, what is the Deal-Grove model is suggesting, right? Deal-Grove model suggests that the oxidation growth is proportional to oxidant pressure, we have seen, right, correct, Cg, right, partial pressures. Growth rate is faster for 111 surface than 100, what does this mean? So, initial growth, let us say this growth rate dx by dt, what is this dx by dt, depends on the Ks initially, correct. Now, what is this Ks depends on? Surface reactions, right. Now, we all know that the number of bonds available on the 111 surface is more compared to 100 orientation, that means the energy required to break that will be less. So, the reaction kinetics will be different from 111 surface compared to 100 surface, and for 111 surface it is more compared to 100 surface, right. This is what this Deal-Grove model is also suggesting, right. So, we have discussed this point, partial pressure of the this thing, and I will leave it to you just to think about this one. This comes under segregation coefficient, whether impurity want to stay inside or not, something like that, right. Then doping concentration, surface reaction coefficient, heavily doped oxidized get oxidized rapidly, alright. So, this is what the conclusion that we can draw. So, let us look into some problems. Now, this is a very typical problem, like when a thermal oxide of thickness 500 nanometer is grown on a silicon wafer using either wet oxidation reaction, what is the thickness of the substrate that is consumed? We have discussed, right. So, if you want x thickness of silicon dioxide, then 0.46 x will be consumed and 0.54 x is consumed on top of that, I mean is formed on top of this, right. So, what is the question? They want when a thermal oxide of thickness 500 nanometer is grown. So, already they have grown 500 nanometer, here x is 500. So, what is the thickness that is consumed, right? So, it is 0.46 x, this is 0.46 into 500, whatever the number that comes up, that is the answer, right. So, this is the answer, 230 nanometer, right. Next, now I told you one more thing, Ks is dependent on temperature, D depends on the temperature, right. Ks can be modeled as K naught e power minus Eg by Kt, D can also be modeled as D naught e power minus Eg2 by Kt. Right. So, instead of K naught here I can write C naught C1, right. For B they are saying C1, right. Right. Now, if you look at like see B depends on D, right, B by A depends on Ks, right. Now, what is this? We have already seen Ks something, right, Ks Ng by Ci something, B is 2 Cgd by Ni, B by A is Ks Cgd by Ni, means B by A depends on temperature, B also depends on temperature, but they are different, okay. Now, B by A depends on surface reaction kinetics, B depends on diffusion kinetics, right. Now, accordingly you have the values here, right. So, B can be modeled as C1 e power minus E1 by Kt, B by A can be C2 e power minus E2 by Kt. That is where they are connected, okay. So, do not think why we are suddenly jumping into this B by E and how the dependence of temperature has come into picture. So, let us ignore that. Okay, let me erase all the ink, right. Now, what is the question? Now, please check the table. Okay, let me take my pen. Please check the table for the values related to 111 silicon oxidation kinetics. Okay, this is for silicon oxidation. Let us consider dry oxidation is used in thermal oxidation process at 1000 degrees. So, the temperature is 1000 degrees. So, here you have to take everything in absolute values. So, 1000 degrees is 1273 Kelvin, and find out what is the value of B by A and B. So, B by A according to this table 111 growth, right. Now, B by A here, right. B by A is C2 e power minus E2 by kT, right. So, K is a Boltzmann constant, and it is around 8.821 something into 10 power minus 5 electron volt per Kelvin, right. You can find out that value, and you know the E2, this is 2 electron volt divided by this one, then C2 value is already there. Now, B is also there, C1 e power minus E1 by kT, right. So, if you know these values, substitute in that and then you will get this, right. Now, one more thing is interestingly, if you see this point here, all C2 values you see should be divided by 1.68 for 100. See, for the corresponding values for 100 silicon, all C2 values should be divided by 1.68. Why only C2 values should be divided by 1.68? Why not C1? You might guess it right. See, B by A depend on Ks, B depends on D, correct. Diffusion really does not matter, what is the orientation, but Ks matters, right. If 111 is there, you will have different Ks, 100 is there, it is a different surface kinetics, right. So, for 100 we know that it is less number of bonds available for breaking, right, obviously Ks will be less, that is the reason why they are telling you to divide by 1.68 only for B by A, it really does not matter for B, right. Then next problem. So, a dry oxidation process needs to be designed to grow 200 nanometer thickness of oxide on 111 wafer. Thickness that they are looking at is 200 nanometer. Try to convert everything into micrometer, then that will be easy because these are in micrometer square per hour, the units you will look at. Suppose that process integration issues requires that a temperature of no higher than 1000 degrees. So, your temperature is 1273 Kelvin. What is the minimum time required to obtain the thickness? So, what is the time? So, what is time? You have x square by b plus x by b by a, that is equal to t, right. Oh, sorry. Now, you need to find out t. You substitute these values. What is b value? You find out what is b value. B value is from this, okay, you can find C1 e power something. If you look at it, if you find the b values you already found, right. So, you substitute x in this 0.2 micron, then you know already we got the b values right here 0.0012, 0.00752. You substitute that in this equation, then finally you will get 6 hours 30 minutes. Now, one can do same thing for wet oxidation as well. Okay, this is a dry oxidation, and find out what is the value of T and figure out for yourself whether the wet oxidation time is less or dry oxidation time is less. So, if you do the same calculation, T wet time required for wet oxidation is less than time required for dry oxidation. That is why this Deal-Grove model is extremely popular. I think we are coming to the end of this. So, the thing is we have covered multiple aspects. We have seen how the flux F1 and F2, right, where how they will balance with each other. Then we try to form a mathematical modeling called Deal-Grove model, and we have looked at some problems, right. So, thank you, see you again.